This is the Tepid Coder. Today I want to talk about some C and C++ grammar. This will be some pretty basic stuff. So, I'm trying to think of little gotchas that I want to bring up first before people really get too deep into the language. I know that some of the videos I'm doing are kind of scattered at all different levels. Right now they're pretty basic to intermediate, but I do want to do some lower level stuff too, and this is one of those videos. When I say lower level, I mean like more novice level. I don't mean lower level as far as like assembly or something. Maybe I can get to that someday too, I don't know. But anyway, one thing I want to talk about today is scope. So you need to find a variable. Let's say I have an integer up here. Let's call it int a, right? And when you define a global, it's automatically initialized to 0. I guess that depends on the type. Things get kind of complex with class objects and things, but for primitive types, it's going to initialize them automatically. If you define something in here, though, let's also call it a. This is not going to be initialized. It's going to be random memory. Well, I guess technically it's not random. It's based on what's pushed onto the stack previously from whatever function call came before. It's effectively random, though. I mean, I wouldn't probably use it as a random seed, but you can just look at it as an unspecified value. So you want to initialize values you define within functions. Any value you define outside of a global context, like up here, it means the whole program can see it. At least the whole object file can see it. Not only can the whole object file see it, but if this is also defined in a different CPP file, there's going to be a clash because the linker is going to see the same variable defined in two object files. So that's actually an issue. You can define it static, and static, when it's in this context, means that it's only going to apply to this object file. That's also true of functions. So if I do static int foo takes nothing, right? We'll just, it does nothing, right? I guess it has to return something, so return 0, whatever. This function is only going to exist inside of this object, and you can have an object that has the same function name as this one, and same type and everything, or even different types and stuff, and it won't matter, because this isn't going to be exported to a different object with a symbol that can be linked with, right? So sometimes it's kind of nice to keep things encapsulated in C by making the functions in that module, or that CPP file, that compilation unit, whatever you want to call it, keeping it within that CPP object file. Anyway, let's not worry about this for right now. I'll get to that in a second, though. Anyway, what I want to talk about right now is scope. So the whole project can see it. So this function could reference a if it wanted to. What do I say? A function in another object file, if it weren't static, could also reference it. This function can reference it, but I'm right down here, I'm defining another variable, also called a, of the same type. Now what happens is, every time you see a curly brace, you're starting a new scope. That's true for functions, it's true if I just do this. I'm not even like doing a for loop or anything. Like here's 2 new scopes, right? And what happens is, every time you start a new scope, things inside of that scope can be referenced only within that scope or a deeper scope. And if you define something that has the same name that already exists elsewhere in a new scope, whenever you reference a variable by that name, it's going to check the closest scope first. So the closest scope, it's going to check up to this right here to try and see if it finds it. So say if I say like a plus equals 1, or yeah, like that. What it's going to do is going to say, okay, it's trying to add to a. Where's a? Let's look back until we find the nearest scope. Okay, this scope's right here, so it has to be between here and here. And it's going to find this definition right here. If I hadn't defined that, it's going to say, okay, check the nearest scope, nothing. Okay, what's the wider scope? It's the whole file, because it's global, and it sees this. So it's always going to use the one that's closest in scope. So what I want to show is, like, I'm going to actually assign this to value 7. I'm going to say, I'll do this. I'll start a new scope here. I'm going to say a is 0, a plus equals 1. Let's print out the value of a. So a, d. We're going to say, I don't know, a. And I'm going to stick to what I always say. You should probably use standard int. This is always what I do. So I'm going to actually call this like a uint 8t. I'll give it a crappy name, a, I don't really care. Uint 8t. But, just to show that I do care about that, and that's how I code. I will use, cross-platform compatible types. So the next thing I'm going to do over here is I'm going to print it out again. I probably could have just copied this, but whatever. I'm in too deep. In fact, I'm also going to do this. Types of h. It's bothering me too much. I'm going to do this the right way. It's unsigned 8. Okay. Yep. Oops. Unsigned 8 integer. So what I wanted to show here is that we have one that's supposed to be a 7. Over here, we're defining a new one at 0, adding 1 to it, so this is going to print a 1. We're going to end the scope, so this variable is going to disappear off the stack. And the one we're actually referencing is the one that's closest in scope now, which doesn't include this. It's going to go back to this, because we're back to this scope right here. It wasn't defined in this scope, it was defined one deeper. Or 1, 2 in. It's defined 2 in. And right now, where are we? We're 1, 2, 1 again. So we're 1 in. What's the closest to 1? Well, there's nothing defined in this scope over here. Like, this is the whole function right here that it sees. So it has to go back at previous scope, but it's going to see this. So I'm expecting it to print 1, and then it's going to print 7, because it's going to see this one. Let's try it out. Let's see what happened. Oh, it has to return it. Oops. It does return it. What is going on? Oh. Well, that would do it, wouldn't it? Okay, so 1 and 7, like I said. Now, this is also true of any other function that I make, so I'm just going to say void foo, whatever. I don't really like using the name foo, because it's not descriptive or whatever, but I can also reference a here, too, so I just want to show that. A, so I'll say foo, so you know it's coming from foo, a, and I'm going to do, alright, oops, wait, god dang, okay, a, and over here I'm going to call foo, and 7, 7, okay. Now, next thing I want to do is I want to show you something else. So if I make an integer value, let's say I call it int b this time, I'm going to say b equals 2. And then I'm going to say b plus plus. Let's do that. So I don't just want to print a anymore. I want to print a and b. So let's do that. I'll do this. I'll say semicolon b colon whatever. It's also a. This isn't int. I'm going to do a. I'll keep it the same. Yeah, I'll do 32, whatever. 32b. Why not? U32. Okay, so it's going to make this variable. It's going to print it out, then it's going to increment it 3, and nothing's going to happen after that because we're not really doing anything with it. So I'm going to call foo twice now. So you can see A7, B2, same thing. But what I can do now is I can call this a static variable. So now static, if you use it inside of a function for a variable, it's going to mean that this variable persists. It has a lifetime outside of this function. So every time you call this function, it's going to use the same static variable. This has some other implications with threading that are kind of bad. So like if you have the same thread hitting this over and over again, there's going to be a race condition where each thread's trying to use the value, and one might be writing to it while the other one's reading from it. So maybe, I don't know, every time you call it, it increments the value. It tries to use it with something and increment it. Well, both functions could see it being 3 at the same time, and both write the next value 4 to it, which is bad, because it should be 3, then 4, then 5, if 2 threads are hitting it. But there's a race condition. So what you could do instead of static in that case is you can actually use this new type called, or new, qualifier called thread local, and that'll make it thread safe that way. Anyway, I'm not going to use that here. I'm going to use static. So because this means that this is essentially global, but it's also encapsulated within the scope of this function, every time this function is called, this same value is going to be used. The initial thing you set it to is only what it's going to be the first time. So the first time you run this function, it's going to set b to 2. Every other time, it's like having this. Like it's pulling it from somewhere else. It's just going to use the value that it's already set to. So to show you that, we're going to print b is 2 the first time. The second time I call foo, it's going to have been incremented. So it's going to print 3. So I'm just going to show that real quick. See that? And I guess I'll show the thread local version too, just because, why not? There you go, same thing. Thread local is actually really slow though, because it's wrapping everything in a mutex, which makes every thread have to wait its turn to access the variable to be able to read and write from it. So yeah, if you are never going to have a second thread hitting the function, you should probably use static instead. But it's something to think about. What else do I want to talk about? Some basic C stuff here. I think I'm going to talk about, now that I've done scope, let's actually get out of here. I'm going to rename this to scope. Let's make a new one. I'm going to call this, I don't know, syntax. Let's talk about some syntax. I'm not actually even going to... should I write a... I guess I'll write a project for it. Why not? Doesn't really matter. Won't take that long. Let's like continue to type poorly, then it'll take a while. Standard lint apparently. Okay. Types of each. Main, void. Look at that. That time I even returned an integer. I can post you. Doing good this time. Okay. So unit AT. Let's call it just A. I'm using really crappy variable names right now because I'm just trying to show stuff. So when you want to set a variable equal to something, obviously you just use equals. Now A is equal to 2. So if I were to print it out at this point, you know, fprintf, set it out. I were to say A is whatever, PRU8, not 7. No 7-bit integers in my house. Okay, so that's going to show 0, and over here I assigned it to 2, so now it's going to show a 2. Anyway, you can also do things like A equals A plus 1. So whatever A was, A is now 1 higher. So A is 3 now. I could also say A plus equals 1. So whatever A was, it's going to be 1 higher than it was. This is the same thing as saying A equals A plus 1. If I say like plus 17, same thing. A equals A plus 17. So it gets 17 higher. That's what that means. You could do the same thing with like minus equals. So minus equals 1. So it's the same as saying A equals A minus 1. So that's kind of nice. You can also say A divided by equals 2, right? So A equals A over 2. You can do A times equals 2. So A equals A times 2. So you get 2 times higher than it was. You can also do it with bit shifting. So bit shift equals 2. So that's kind of the same thing as A times equals 4. Or A equals, let's see, A times 2 to the power of 2. Yeah. In fact, I kind of think of it as being like 1 times 2 to the power of 2, but I mean, whatever, it doesn't matter. You can do the same thing the other way. So A right shift equals 1, so it's basically A over 2, A equals A over 2. Or you could say A equals A bit shifted to right once. These are all the same thing. A equals A, so basically A equals A to the left twice. Same things. You can also do it with the modulo operator, so take the remainder of something. So A equals the remainder of A and the remainder of A divided by 2. So A equals A mod 2. Percent sign means modulo. So, which means the remainder of dividing... Yeah, let's just say the remainder. Operation. So like, I should probably explain that just in case you don't know what a modulo is. So if you have like, let's say 3 over 2, right? That's going to be 1.5. Or you could say equals 1 plus 1/2, right? But what if I want to know what the remainder is? Well, 3 goes into 2 once, then you have 1 left. So the remainder would be 1. So you could say it also equals 1 R1, right? So the modulo would be 1 if I did that. So that means 3 mod 2 equals 1. So that's what's left over when you divide. Okay, and obviously if you can do plus equals, it means you can do it equals this minus this equals this plus this divided by this times this, whatever. What else? Let's see, there's bitwise operations. I already showed the left bit shift, right bit shift. You can also do a binary OR, which is a pipe. So a pipe equals, which is OR equals, say equals 1, which means like say you have a byte like I do, it's 8-bit integer, which means I have 1, 2, 3, 4, 1, 2, 3, 4. Let's say that got the value right now. I'd have to do some math to find out what it is right here, but I don't really care. Point being, say it's all zeros right now. If I OR 1, it's saying I'm doing a binary OR with this value right here. And that's basically just going to add that bit in if it's not already set. If this is already set, it would do nothing, but because it's not set, it's going to put that value there. So any bits that aren't set in this and are set in this are going to be added to it. That's all it is. And if I do it and equals, let's say 0xff. So ff is basically the max possible value I could represent. Because you imagine you have like base 10, the values are going to be 0 through 9 for each digit. So say I gave you 3 digits and you put 9 and 9, that's the max value you could put there. you'd need more digits to represent something higher. Same thing with hexadecimal, but the max value instead of 9 is f. So if I do 3 f's with 3 digits, that's the max possible value you can represent. Anyway, an AND, what that does, let's pretend I have, I don't know, 0, 1, 0, 1, 1, 0, 1, 0. And let's say the other value, I'm ANDing it, is going to be 1, 1, 1, 1, 1, 1, 1, 1, because it's all set. It's the max possible value. What happens with AND is it checks to see if both bits are set in the corresponding positions. So this bit right here is checked against this bit. So that one is not set, so equals 0 in that case for that bit. Let's check the next bit. This one is 1, this one is 1. So that one is set, okay. How about the next position? This one is set, this one isn't. That's going to be a 0. Okay, next position. 1 here, 1 here. So that is set, cool. Now we're at the higher nibble. So this is a 1, that's a 1. So that is set, okay. This is a 1, that's a 0. So that's not set. This is a 1. And this is a 1, so that is set, okay? And this one is a 1, and that one is a 0, so that's not set. So this is what you would get right there. Okay, the other thing you can do is XOR equals. So the caret is here. So if you XOR something, let's XOR by 0. So XOR is a bit confusing. I like to think of it, if the bits are different, then the value of that bit becomes 1. If the value of the bits are the same, it becomes 0. So I think I'm actually going to bring up a truth table for it, because I think that'll be good. So XOR truth table, so you can kind of look at it. XOR gate, I want the truth table. Here we go, this will work. This is from Wikipedia here. Let me move it over, please. Okay, thank you. So right here you have a truth table. If you have 0 and 0, it becomes 0. If you have 0 and 1, it becomes 1. 1 and 0, it becomes 1. 1 and 1 becomes 0. So, like I said, if they're different, you get a 1. If they're the same, you get a 0. So 2 0 is going to give you 0 because they're both the same. 2 1s give you a 0 because they're both the same. 0 1 is different. 1 0 is different. So that's how I remember it. I don't know if it's the best way to remember it, but it works for me. Anyway, let's take a small example. I don't want to do this with a huge long drawn out example, but let's just do like 0 0 0 0 0 0 0 1, and we'll XOR it by, I don't know, 1 1 1 1 1 1 1 0. Okay, that equals. Let's see, which ones are different? So I'm going to look at this one and this one. Are those different? Yes. How about this one and this one? Yes. In fact, they're all different. I basically intentionally made them so they're all different. So it's just going to be all ones. Okay? One thing you can do is if you want to invert all the bits, you could just always XOR something by the max possible value. So right now the max possible value of an unsigned 8-bit integer is 0xFF. If it was a 16-bit integer, it'd be FFFF, right? You have 2 bytes, right? These aren't case sensitive, which is kind of interesting. But if you had 4 bytes, it'd be that, right? If you had 6, double that, you know? 1, 2, 3, 4. So that would be a 64-bit integer. You could invert all the bits that way. So that's nice to know. Anything else that's interesting? So I talked about scope. I talked about some basic arithmetic operations, adding, subtracting, multiplying, dividing, bit shifting, and or modulo, XOR. I haven't done complement, so you can also do this. If you want to invert all the bits, you can say equals the complement of A. That is the same thing as saying that, you know, A XOR equals 0x a bunch of f's, you know, however many there are in the size of the type. So that's kind of a nice little shortcut there. And the last one you can do is A, like not equals A, for example. I don't know if you can actually do that, but you can say it equals not A. I haven't tried not equal. I'm going to see if that compiles. I'm curious now. Let's see, G++ syntax.cpp shows syntax. It likes it. Wow, you can do that. I learned something. That's interesting. I didn't know you could actually do that. But it's kind of nice to be able to use not, because what not does is it says if anything but 0 become 1, right? Otherwise, 0. So anything that's not 0 becomes 0, and 0 becomes 1. So it's basically, if this was true, it's now false. That's kind of what you use it for. You negate the truth of something. Anything else interesting to talk about? I know. Something else I want to talk about, actually. I talked about primitives earlier. And you have types like, you know, int at. Let's call it I. What you can also have is something called const. That means once you set this value, like 17, if I try to say I equals 5, it's going to complain because it's constant. You can't mess with it once you've defined it. Okay, so I'm going to try and do that, and it's going to complain. See? Assignment of read-only variable. Now, if this wasn't const, that would work. But const is just when you want to make sure something's not manipulated. It's kind of good to make sure that if someone else is working with your code, they don't accidentally mess with something that they shouldn't be. You can also do this for parameters to functions. So if I say something like, wow, why did that work? That shouldn't have compiled. Huh. I don't know how it was able to work without that pound sign there. Anyway, let's say I make a function, call it foo, just because I'll say const I. Yeah, const int I. I don't even like int. Let's not do that. Int 8. In this case, same thing. It's passed as a constant, so I can't manipulate the value if I can speak English. If I try to do that, it's going to complain, right? So I'll try that. See, assignment of read-only parameter. So parameter in this case. Now, something interesting here. If you have something like a pointer variable, I want to actually talk about this. Maybe I should do it in a different video. I think I will. I'm going to talk about pointers in a different video, because constant pointers, although I do want to mention them now, act a bit differently. So I'm just going to give a brief overview of constant values or qualifiers for pointers real quick, but I'm not going to explain exactly what pointers are and how they work yet. I'll do that in a different video. So I have a pointer, let's call it P. It's a type character, right? It's a character pointer. Now for this, even though it's constant, I can say P++. This is because I'm not actually changing the value of the variable. What I'm doing is I'm looking at the next character in memory. So I'm saying, like, right now I'm pointing to a character somewhere in memory. If I increment, what I'm actually incrementing is the pointer. The pointer is just some address. Now, if I did something like this, the value at P increments, that would be a problem, because then I'm actually incrementing the pointer. But what you can do is you can actually make it so that this is an illegal operation as well, by saying not only is this constant, like the data it points to is constant, but I can say the pointer itself is constant. That's what this is doing. So now I can't even do that. So watch this. That shouldn't have worked. Maybe because I'm not actually calling the function. Let's see if that happens. So, foo. Yeah, now it's complaining. Right? No, because it expects a pointer. Dang it. Okay, fine. So let's just say char C, okay, and then I'm going to pass a reference to C. Don't worry about how this works yet. I'll explain in a different video, but I'm basically saying reference this variable wherever it is in memory. And let's say C equals C, the character C. There we go. Cannot convert it to char pointer to constant char. Okay. So that's kind of funny. What I could do, I wonder if, no, I'm just going to say this. I'm going to cast it const char const. There we go. That shouldn't work though. It should be complaining about this because you're not allowed to increment where the pointer points. It should be complaining about that. I don't know why the compiler's not catching that. Because I'm saying this is constant, I can't modify the data inside the pointer, and I can't modify where the character or the pointer points. This should be illegal. Also, if I do this, P equals D now instead of C. That should also be something it complains about. So that one it is. Assignment of read-only location. But I promise you, that's what this means. You're not supposed to change where this is pointing if you add this extra little const star. I don't know why the compiler's not complaining about this line right here. That is absolutely an error. But I am not going to fret about it, I suppose. I will catch you guys in the next one, and I will talk about pointers in that video.